intensity. This is independent intensity of the incident light. Here, the photoelectric current and the number of photoelectrons are directly proportional to the intensity of the incident light. Kinetic energy is independent, but the number of photoelectrons is directly proportional to the intensity of the light. Here, when the frequency of light, which is greater than certain minimum value, even though the number of electrons will not be ejected. So that is, here no electrons are ejected from the metal unless the frequency of light is used, which is greater than a certain minimum value, that is called as what? Threshold frequency, as already we discussed this one. Here, the electrons are also ejected in high vacuum also. And the ejection of the electrons is a spontaneous process. Is a spontaneous process. These are some of the laws of photoelectric emissions. So if we plot the energy of the electron, that is electron energy, and frequency, you can get a line like this, where this is nu naught. And if you plot the kinetic energy of the electron and intensity, just now we told the kinetic energy is independent on that one. So we can expect a question here by giving so many graphs. So one among them, this will be right there. These are the laws of what? Photoelectric effect. And here, the failure of the wave theory explain photoelectric effect. So according to the wave theory, energy is emitted or absorbed continuously by a body. So therefore, any radiation of any lowest frequency is allowed to fall on any metal surface for hours together. What happens? That increases its energy. So therefore, the metal should attain high temperature and the electron should eject from the metal surface, and the energy of the electrons ejected should be increased, but it is not happening. So therefore, the wave theory is failed to explain the photoelectric effect. So this is successfully explained by using Planck's quantum theory. Here, when a photon strikes a metal surface, a photon strikes a metal surface, then it uses part of its energy to eject the electron from the metal atom. And the remaining part of the energy will be given to the ejected electron. So here, the incident radiation is giving energy to the electron to move away from the metal, and that energy is called as binding energy. And here, if this nu naught, if you see this one, the total energy of incident photon is equal to what? Binding energy plus kinetic energy of ejected electron. So for example, suppose the incident photon has the energy which is equal to h nu, and the binding energy is given as h nu naught, and the kinetic energy is given as half mv square. The total energy of incident photon, let us assume that it is h nu, which is equals to the binding energy and the kinetic energy of the ejected light. So from this equation, we can write half mv square is equals to h nu minus h nu naught. So therefore, the kinetic energy half mv square can be written as h into nu minus nu naught. So now we can see this one. So how we see, let us say this is a metal surface. If the light is incident on the surface of the metal and the electrons are ejected. Here, from this expression, what is that expression? Half mv square is equal to h into nu minus nu naught. So for example, to explain this equation is perfectly explaining the experimental facts. For example, if nu is greater than nu naught, that is, if the frequency of the striking radiation is greater than threshold frequency, so the excess energy is transferred to the eject electron as kinetic energy. So therefore, with the increase in the frequency of the incident photon, the kinetic energy of the ejected electron is increased. If nu is greater than nu naught, what happens here? The kinetic energy of ejected electron increases. Here, for example, if nu is less than nu naught, that is, if the frequency of this striking radiation is less than the threshold frequency, then no electron will be ejected. So even though you increase the intensity of the radiation, no electron will be ejected. Why? Because loss of what? Photoelectric effect. So always the incident radiation should have the frequency which is more than threshold frequency. But here the threshold frequency is less. Here the incident radiation has less of that one. So what happens here? Automatically the ejection of the electron will be stopped. So automatically, what can we say? No electron will be ejected. And this, the threshold frequency is different for different metals. So for example, you take a certain metal M, undergoes photoelectric emission when it is bombarded by one photon of indigo color. So always you remember, one photon will eject one electron. Here, for less frequency, even though you apply 2 photons of red color is incident at the metal surface, the electron will not eject. Why? Because the red color has the less threshold frequency. So by increasing the intensity of the light of a given frequency, which is more than threshold frequency, the number of photons will be increased. Now we can see about the Compton effect. Here, when X-rays are incident on certain metal surface, it is found that the transmitted light has more wavelength. Means what is happening? The energy of the X-rays are decreasing. This is observed by a scientist called Compton, and that effect is called as Compton effect. And how can we define? The phenomena in which the wavelength of the radiations scattered by an element is greater than that of incident radiation. Here, to explain the Compton effect, some assumptions are made. That is, a free electron is always present in all scattering material. And a free electron is supposed to be at rest. The collision between the electron and photon should be elastic. So the free electron can only be knocked out by definite amount of energy, that is called threshold energy. So always the energy of incident photon is supposed to be greater than that of threshold energy. So the beam of the photon is monochromatic and it should consist only one single wavelength and frequency. So therefore, the particles like electrons have some relation between the energy, that is E is equals to mc square, where m is given as m naught by 1 minus nu square by c square under root, where m naught is mass of the electron at rest and m is mass of the electron with the velocity v, and c is velocity of light in vacuum. So if we see the effect of Compton effect, for example, this is a metal surface and we are here. This is incident light. This is energy. This is incident photon, that is incident light. Here, this is scattered X-rays. This is scattered electron. Here, the energy which is equals to h nu of the X-rays, and here momentum of this one, here energy will be given by mc square, and here momentum is given by h nu bar by c, and here this is equal to what here, h nu c plus cos theta plus mv cos theta. Here, Compton found that when monochromatic light of X-rays fall on the carbon or some other light element, the scattered X-rays have more wavelength than the incident X-rays. So what happens here? That indicates that the scattered X-rays have less energy than that of incident X-rays. So when X-rays fall on the surface of the element, some interaction between the X-rays and electrons takes place. And because of this interaction, the energy of the incident X-rays is decreased. So therefore, the increasing the wavelength takes place. Here, assuming that the X-rays have particle nature, then applying law of conservation energy and law of conservation of momentum, the Compton shift is given by one equation, that is delta lambda is equals to 2h by mc into sine square theta by 2. Here, from this above equation, we can say that the Compton effect is independent of the wavelength of the incident X-rays. From this equation, what can we understood? The Compton effect is independent of the wavelength and incident radiation, that is X-rays. Here, the Compton effect proves the corpuscular nature of the radiation. So this reaction can also be written as h by mc into 1 minus cos theta. So this can also be called as this delta lambda is nothing but what? Lambda dash lambda. This can also be called as what? Compton shift or lambda shift, wavelength shift, that is. For example, if theta is equals to 0, then cos theta is equals to what? Cos 0, that is equal cos 0 is equal to 1. Then what happens here? Delta lambda is equals to h by mc into 1 minus 1. So delta naught becomes 0. So therefore, there is no what shift in the wavelength. And for example, when theta is equals to 90 degrees, then cos 90, cos theta is equals to cos 90. Cos 90 becomes what? 0. So therefore, Compton shift or wavelength shift, we can write it as 1 minus 0. This is equals to lambda h by mc. This is given by, what is h? 6 Planck's constant, 6.625 into 10 power minus 34 joule second by 9.11 into 10 power minus 31 kgs, that is mass of electron, into, this is 3 into 10 power 8 meters per second. So by simplification, we are getting, this is 2.42 picometers. This is nothing but Compton wavelength. So for example, in the third case, when theta is equals to 180 degrees, cos 180 becomes minus 1. So then this becomes as h by mc into 1 minus minus 1. This becomes 2h by mc. Therefore, this is what? That twice the value of the Compton wavelength. So this is about the Compton effect. And the Compton effect also explains the uncertainty principle. So let us suppose that X-rays are used to determine the position and momentum of an electron. Due to interaction between electron and X-rays, the wavelength of the X-rays increases and hence energy decreases. So why it is happening? Because some of the instant X-rays are transferred to the electron. So therefore, the momentum of electron is changing. So therefore, we can say that the momentum of electron cannot be determined with certainty. So therefore, from this knowledge, we can say that Compton effect is perfectly explaining the Heisenberg's uncertainty principle. And we can see about what Debroy wave concept. Here, according to Debroy, the small particles like electrons which are in motion the small particles which are in motion have wave nature. So this is given by lambda is equal to h by mv, where h is Planck's constant, m is mass of the particle, v is velocity. So as mass increases, the wavelength decreases. Indicates what? By increasing the mass, the particles lose their wave nature. That's why this is applicable for the small particles like electrons. And here, according to Bohr's atomic model, the angular momentum is angular momentum of electron is quantized. That is given by mvr is equals to nh by 2 pi. He proposed what angular momentum of electron is quantized, but he did not explain this. This is one of the drawbacks of Bohr's atomic model. But it is perfectly explained by Debroy. How? Now we can see that one. Here, by interchanging of the terms in this equation, I can write like this: 2 pi r is equals to n into h by mv. So 2 pi r is equals to n into lambda. So what is 2 pi r? This is circumference of a circle. Circumference of a circle. So from this equation, what can we say here? The integral number n of wavelengths can be accommodated in Bohr's orbit. So therefore, what does it mean? There will be always whole number of waves in orbit. So in this state, what can we say here? The electron waves are said to be in phase. This is like this. When MVR is not an integral multiple of h by 2 pi, then what can we say here? The wave should be out of the phase. The electron wave should be out of the phase. That is like this. This is out of the phase. This is in phase. So therefore, what can we say? It will come out of the orbit and hence lose energy. But it is not possible. That's why we can say that always angular momentum of the electron is quantized. This is perfectly explained by Debroy. Now we can go for Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, it is impossible to determine the momentum and position of the electron simultaneously and accurately. It is impossible, means it is not possible to determine the momentum. Momentum is given by P. What is P? Momentum, mass into velocity. The product of mass and velocity is called as momentum. And what is he telling? If we know the momentum, if we know the velocity, we know the momentum. And also we can define like that. It is impossible to determine the position and velocity of the electron simultaneously and accurately. So that we can give one equation, that is delta x into delta p is greater than or equal to h by 4 pi. And as we know P is equal to mv, then we can write delta x into m delta v is greater than or equal to h by 4. There is no delta m. Why? Because the mass of the electron is constant. So therefore, this can be written as delta x into delta v is greater than or equal to h by 4 pi m. When mass of the particle increases, they lose the wave nature. And what is delta x? Delta x is uncertainty in the position of the electron. And what is delta p? Uncertainty in the momentum of the electron. And what is delta v? Uncertainty in the velocity of the electron. So why it is happening? For example, if we know the position, we are unable to find the momentum. And if we know the momentum, we are unable to find the position. How? Now we can explain it. For example, if we want each other, we need light, energy to watch the books or objects, etc. Similarly, for example, the electron is revolving around the nucleus like this. like this in paths. So let us say this is the original path of the electron. So for example, let us assume that at particular instant the electron is at this position. To watch this electron, we have to send some light energy. And the energy of the light should be more than that of the wave. Here, to watch this one, we want to, here electron has some wavelength because it's a wave nature. So the wavelength of the light should be less than the wavelength of the electron. And if that light has less than the wavelength, automatically it should have more energy. And electron is very clever and very fast. It absorbs the instant radiation, that is light energy, and jumps to some other way. That's why we are unable to detect the position and momentum of the electron simultaneously and accurately. So this led to the what probability of finding of the electron. So Heisenberg's uncertainty principle led to what probability of finding electron in the atom around the nucleus. And so this Heisenberg and Schrodinger, both of them proposed the wave nature of the electron, but a scientist Schrodinger, proposed one equation that is called as Schrodinger's wave equation. Here, the Schrodinger considered the electron as three-dimensional wave. In the electric field of the positively charged nucleus. So the Schrodinger considered the electron as three-dimensional wave in the electric field of the positive charged nucleus. So to explain the behavior of the electron waves, he proposed one equation that is called as Schrodinger wave equation. What is that? Dou squared psi by dou x square plus dou squared psi by dou y square plus dou squared psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. Here, this can also be written as h psi is equals to e psi, where this is h operator is called as, it is a mathematical operator. This is called as Hamiltonian operator, where this is given as minus h square by 8 pi square m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Here the solutions of this equation. So he has given some solutions. You can study in detail in the previous of your PG after getting your seat in various universities. Here, the solutions of these equations are called as orbital wave functions. The orbital wave functions are denoted by psi. This indicates what? Amplitude of an electron wave. And here, psi square indicates the probability of finding electron, where a given region of space around the nucleus. So the Heisenberg's principle and his Schrodinger wave equation told what? The probability of finding of electron. The probability of finding of electron. Here, the probability of finding of electron, that is called as orbital. The probability of finding of electron where it is maximum. So the probability of finding of electron around the nucleus in the atom, where it is maximum, where the space around the nucleus where probability of finding of electron is maximum is called as orbital. Here, the space around the nucleus where the probability of finding of electron is maximum is called as orbital. So the orbitals here, you know very well, they are s orbital, p orbital, d orbital, f orbital. So what is s orbital? Here, when L is equal to 0, then that orbital is called as s orbital. When L is equal to 1, it is called as p orbital. When L is equal to 2, then it's called as d orbital. When L is equal to 3, then it is called as f orbital. And if you see the when L is equal to 0, we have here what is this L? Azimuthal quantum number. So now we can see about the quantum numbers. They are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So here these are denoted by N, L, M, and S. By knowing the N value, we are able to know about the L. The N is called as principal quantum, that values are 1, 2, 3, 4, and so on. These values are 0, 1, 2, and so on. This is minus L to 0 to plus L. This is plus or minus half. Here, always L is less than N. L is not equal to N. When L is equal to 0, we have 2L plus 1. That is, we have only one M value. So therefore, we have only one type of s orbital. And here, the shape of s orbital is called as what? Spherical. And p orbital is a dumbbell. and a d orbital is double dumbbell, f orbital is complex. That is a four-fold axis. Okay, like this, we can see about the orbitals. So with this, we can conclude. We can see some of the problems in the next class. Thank you. We can stop this.